So, how does a GPS work? I'm going to show you using simple line of sight, straight line equations, how it works and when it doesn't work. Very simple. The math is easy, but it's very important that you understand how GPS works and when it will not work. Here is a simple GPS system where you are in this user, you're in that airplane, the B2 in the center. And we want to figure out where we are. So we use these lines of sights, There's one to one satellite, there's another line of sight, there's another line of sight. And you need, if you have 4 of these lines of sights, the different satellites, then you can solve. And they're all straight line equations. And those equations will intersect at the user position. So if everything is working just right here at the user position, these 4 lines of sights will intersect. Now the satellites can be spread around wide open. The satellites can be spread around wide open, or they can be tightly compacted. And what I want to show you today is that when they are tightly compacted like that, this intersection point becomes ill or undefined, and you end up with no solution for the GPS. And when the satellites are widely separated, then you end up with a good solution for your GPS. And that solution is called the geometric dilution of precision, or GDOP. A low number for GDOP is a good solution. That means a low number means that these satellites are widely separated. A high number for GDOP, like 10 or bigger, means don't use it for navigation at all. So let's take one of these lines here. Let's take this line and see if we remember how we can make an equation out of that line, mathematically speaking. Well, we might put it on graph paper, and we remember the equation looks like y equals mx plus a constant, and that constant is going to be the y-intercept. In other words, when x is equal to 0, the y-intercept, so the constant is going to be 1, and the m is the slope. Remember, that's the rise over the ground, or the pass, and this thing rises twice as fast as it moves across. So the rise over the run here, or the slope, would be 2. So we know the equation for this line is y equals 2x plus 1. That gives us the equation for one of the lines. So what if we have another satellite? Well, if we have another satellite, well, now this one is a little bit of a shallower slope, the shallower slope line here. So it goes over 1, 2 for every 1. So it rises 1 for every 2 it goes over. So its slope, or m, is going to be 1/2. And of course, the y-intercept is still going to be 1. It's still going to be 1 for this shallower line. So we can see pretty much from the graph that these are going to intersect at a user position of 0x and 1y, or 0x and 1y for the intersection point. So we know what the user position is going to be. What does the GPS do to combine these two sets of equation, right? So that it gives us the user position, the intercept point, every time. And we can see that the line intersection point depends on the slopes, right? For if the slopes ever match up, then the lines of sight will either be parallel and never intercept, or they'll be everywhere equal and always intercept. And you might have learned this in high school as what's called direction cosines. It's exactly the same thing. So can we get a computer to solve this problem for us and give us the point x equals 0 and yi equals 1 for the intercept point? Well, the computer uses a matrix, but let's go through it algebraically first, because you might remember that in the better. If we were just to solve for the two equations to find that point, we'd write the equation of a straight line. And the equation is y equals mx plus c. And for the first line, we know that m is 2 and c is 1. For the second line, you know the slope m2 is 1/2, and c2 is also 1. So we can back substitute that second equation into the first and get our answer for the xi point. And it'll turn out that xi will be equal to the difference between the two constants, c1 minus c2 and m2 minus m1. Well, it's okay for C1 and C2 to end up to be 0 in the numerator, but not in the denominator. So remember, you have mathematical anarchy and total chaos if you divide by 0. I hope you had a math teacher in high school who told you that. So here I am putting the two equations in matrix form. And on the left, you can see the format you might see it in a book, where the matrix capital A has 4 elements in it, the slopes, and then the vector C has the 2 constants in it. And I'm just showing you here that if you put it in matrix format and solve for it, you're going to get the same answer, which I call QED. That's a Latin for thus it is proved. Now, the question is, what does the matrix solution look like for a 2 by 2? Again, you would never do this by hand. No one does these things by hand. But the computer, if you can ask a computer to give you the inverse of this matrix and just put those 4 numbers in and say, okay, what's the inverse? Well, the inverse is going to be what's shown on the bottom left there. And notice the denominator has m1 minus m2. Wow. So the inverse is going to blow up on you if the m1 and m2 are equal, because you're going to divide by 0 again. Your solution will blow up. You'll have math, chaos, and anarchy, which you not want to have, especially for GPS. So if you're going to use a matrix, then you would find your A matrix and go through the solution by putting it into a computer. Now, in a GPS sense, it uses a 4 by 4 matrix. We're doing it for a 2 by 2. The 4 by 4 solution is not known analytically. In other words, I can't put symbols in there like I can for a 2 by 2. But I'm going to show you the solution for the 2 by 2 A inverse solution that automatically gives you the answer, which you can only get numerically if you are using a 4 by 4 computer. Notice everything else is a vector. So my vector x that I've got shown there on the left is actually my unknowns, and the vector c are the 2 constants, c1 and c2, which are both equal to 1. So if I put those into a computer and say, okay, get the inverse, give me the inverse, and then multiply the inverse times the vector c, and that'll give me my unknown answer for xi and yi. So there's the inverse. I'm showing you to as A inverse, and if you multiply it times the constant vector, you'll see that once again in the denominator you're going to end up with chaos if the slopes are equal. And if you multiply out the matrix solution, you'll get the same solution that you received using algebra. So you'll find out that if you were to write it out, you'll get the first solution is going to be equal to xi equals 0, and the second solution, y is going to be equal to 1. Okay, so let's review now what you need to know and remember about GPS positioning. The first thing is that for each line of sight to each satellite, you can solve for a variable. You have 3 variables in position and 1 for the error in time. So you need 4 satellites to solve for those 4 things, the 3 variables in position and for time. And we went through a few things that are important to remember. The first thing is that the line of sight is crucial. You must have a line of sight. It's a radio. GPS is a radio, and so you must have that. The second thing to remember is that if the position is at the intersection of the line of sights, or what we call the direction cosine lines. Your position is at the intersection of it. The third thing to remember is that when the satellites bunch up like this, you're going to have a horrible solution or no solution, because you'll be dividing by 0 when you try to take the inverse of the matrix. Now, we did a 2 by 2 matrix, but you could have had a 3 by 3. The GPS solves a 4 by 4 or higher matrix. And the last thing to remember is that when the satellites are spread out, when they're spread out like this, you get a very, very good solution. So the next time you look at your cell phone, the next time you use your cell phone, remember that it knows where all the satellites are that are up there. It knows where all the satellites are, and it picks the ones that are separated best to give you the best accuracy of the solution. An accuracy that's called the geometric dilution of precision, or GDOP. And a GDOP of less than 5 is good. And it knows that number. It has that number inside. Okay, that's it. Thank you.